Hello everyone, this is lecture 12, functions of several variables. In the last few lecture notes, we have talked about vectors and the vector value functions, which took us into three-dimensional space for the first time. Starting from this lecture, we step into three-dimensional space along a different path by considering function with several independent variables and one dependent variable. All the familiar properties of single variable functions such as domains, graphs, limits, continuity, and derivatives have generalization for multivariable functions, although you will see some subtle differences and new features. For example, with function of several independent variables, we work with partial derivative, which in turn give rise to directional derivative and gradient, a fundamental concept in calculus. Partial derivative allow us to find maximum and minimum values of multivariable functions. Later on, we define tangent planes rather than tangent lines that enable us to make linear approximations. And then at the end of this particular section, we're going to look into optimization problem in several variables. For this particular lecture, hopefully at the end, you could be able to recognize a function of two variables and identify its domain and range. You could learn how to sketch a graph of a function of two variables, but technically I'm going to show you the website geogebra.org again, how to input the information and let the machine work for you. And then we learn how to sketch level curves of a function of two variables. And the last part of the lecture is to learn about a function of three variables and how to identify its domain. So first I want to give you the definitions of function of two variables. So a function of two variables written in the form of z equal to f of xy. Map each order pair of x, y in a subset D, which is the domain in this case, of the real plane R2 to a unique real number z. D in this case is the domain of the functions, and the range of f is the set of all real numbers z that has at least an order pair xy in D such that f of xy equal to z. So what you see in single variable functions is the setup of y equal to f of x, where you have that y is the output or the dependent variable. Or output value. And you have x in this case is the independent variable. Or the input value. Now, when we move on to function of two variables, the idea of two variables is that you have two independent variables. So you have z equal to f of x, y for x, y independent variables, or the input values. And z in this case is the dependent variable. This is the visualizations of the definitions of function of two variables. So a function, again, a function of two variable z equal to f of xy, map each order pair xy in the subset D. So this is the domain of the functions of the real planes R2 to a unique real number z in the range. In general, functions of two variables are written explicitly in terms of z equal to f of x, y. So this is called explicit form. But it can also be written in implicit form as capital F of x, y, and z equal to 0. So this is implicit form. And the concept of domain and range carry over directly from function of single variable. We will learn how to define the domain and range of function of two variables later. But now let's take a look at the graphs of function of two variables. The graphs of function of two variable again follow the same concept covered in single variable calculus. So function of two variable must pass a vertical line test. That is, if the graph intersects a vertical line at more than one point, then the graph does not represent the functions. For instance, in this case, you have two different graphs. The first one is called the ellipsoid. So this is not a graph of function. because it fails the vertical line test, right? The graph intersects the vertical line at 2 points. Whereas you have this image here represent graph of a paraboloid, and it is the graph of the function. And this function has the equations of the form z equal to ax squared plus by squared, for a and b are constant, x and y are independent variables in this case. We will talk about GeoGebra a little bit later as we deal with finding and sketch the domain of the functions and visualize the function that way. So how could you find the domain of the function? Again, the information that you learn in single variable calculus going to directly apply to function of two variables, such that the domain of polynomial functions going to be always from negative infinity to positive infinity. The domain of a rational function, that is, you don't want the denominator to be equal to 0, and the domain of the square root function, that is, the expression under the square root or even root for that matter, has to be greater than or equal to 0. The domain of a log function, that is, the part attached to the log function, has to be greater than 0. The domain of an exponential function is always all real numbers. We're going to look at the following example. So we want to find the domain and range of the following function of two variables. So the first function of consideration is f of xy equal to 3x plus 5y plus 2. So in this case, x and y are linear functions, in a way polynomial functions, so therefore there's no restrictions on x and y, and thus the domain is from negative infinity to positive infinity. So you say that since there are no restrictions on x and y, we have, so the domain of the function I denote as d sub f is equal to the set of all the point x, y in R2, or you can just basically write R2 for the answer. Now for the range of the functions, again, there's no restrictions on x and y, so it take in any value of x and y and produce all the real values for z. So the range is the set of all values of z in R such that z is equal to 3x plus 5y plus 2, and the range of the function is going to be equal to the real line. So here again, you take in two independent variables and you give out one dependent variables. Okay, so that is the domain and range of the function of the form f of xy equal to 3x plus 5y plus 2. Now we're going to move on to the functions of the form g of xy equal to square root of 9 minus x squared minus y squared. So again, as I mentioned earlier, all the information, all the rules in single variable calculus get applied to function of two variables. In this case, you have a square root function, that is, the expressions under the square root has to be greater than or equal to 0. So here, to find the domain of the functions, you have that 9 minus x squared minus y squared is greater than or equal to 0. And you're going to solve for x squared plus y squared. That is, x squared plus y squared going to be less than or equal to 9. So the domain of the functions is equal to the set of all the point x, y in R2, such that x squared plus y squared less than or equal to 9. So how could you visualize this particular domain? Right, it's not a real number, it's not an interval, it's actually going to be the circle center at the origins with the radius less than or equal to 3. So here we can plot the domain of the function as follow. Instead of writing the domain in terms of the interval notations and plot that on the real line, here you have this is y, this is x, this is the origins, and you have the circle center at the origins with radius 3. So this is 3, 3, negative 3, negative 3, and the domain contains all the points inside the circle, including the boundary. Okay. Now to find the range of the functions, because the range, which is the output in this case, I'm going to denote this as z. So z is equal to the square root, and square root has to be always greater than or equal to 0. Now to find the range, you're going to start with something in the domain. So that is x squared plus y squared less than or equal to 9. And this x squared plus y squared is going to be greater than or equal to 0. Now we're going to manipulate this inequality so that it mimics the functions that we have. I'm going to multiply -1 for every term in the inequality. When you do that, the inequality sign will switch directions. Now you have -9 less than or equal to negative x squared minus y squared less than or equal to 0. Again, we try to mimic the function here, so you get negative x squared minus y squared already. Now you just need to add 9 into the middle term here. By doing that, you basically add 9 for every term in the inequality. So you have 9 minus 9 less than or equal to 9 minus x squared minus y squared less than or equal to 9. So technically, you get 0 less than or equal to 9 minus x squared minus y squared less than or equal to 9. And then you can take the square root of this inequality and you get that this is 0 less than or equal to square root of 9 minus x squared minus y squared less than or equal to 3, or this is technically z between 0 and 3. Therefore, the range of the function is to set up all the value of z on the real line such that z is between 0 and 3, and including the endpoints. In the interval notations, the range of the function is between 0 and 3. Now, for the next function, you have f of xy equal to ln of x plus y. So similar to single variable calculus, when you find the domain of the log functions, you do that x plus y has to be greater than 0. So you can solve for y in terms of x as y is greater than negative x. So the domain of the function is to set up all the point x comma y on the 2D planes such that y is greater than negative x. So let's visualize this domain of the function. So you're gonna plot the 2D plane or the xy plane again, and you're going to plot the functions y equal to negative x. Now you don't have the equal sign, so instead of a solid line, I'm gonna use a dotted line. This is the line y equal to negative x again because there is no equal sign in the inequality. So instead of solid line, I'm going to use dotted line. Now the domain of this function is all the points in R2 such that y is greater than negative x. So therefore, you just choose this part of the plane as the domain of the functions. And you're not going to choose this part because this part tells you that y is less than negative x. So this is the domain of the functions. Now for the range of the functions, as you remember from single variable calculus, the range of log function is from -infinity to +infinity, and it's going to be the same in this case. So the range of the function is from -infinity to +infinity. Let me move on to the next function. Again, we have a log function, so the domain of the function can be solved at xy greater than 0. So when you have x times y greater than 0, there are two situations. So this implies that both x and y are positive, or both x and y are negative. So this implies that there is two scenarios, x greater than 0 and y greater than 0. Or there's a second scenario that x is less than 0 and y is less than 0. So in general, when you write the domain of the functions, you're going to see that this is the set of all the point x comma y in R2 such that x, y greater than 0. So this two scenario, we can actually visualize that. So how could you do it? You again plot the 2D plane or the xy plane. So this is x, this is y, this is 0. See, in the case of x greater than 0 and y greater than 0, that means you choose the first quadrant of the xy plane. In the second scenario, you have x less than 0 and y less than 0. So this is the third quadrant of the xy plane. Therefore, the domain of the function consists of all the point x comma y in the first quadrant and in the third quadrant. And this is logarithmic functions. Therefore, the range of the function is all real numbers, starting from -infinity to +infinity. Now let's move on to the next example. In this example, you have a square root function again. So the domain of the function is 36 minus 9x squared minus 4y squared greater than or equal to 0. So I'm going to move 36 to the right hand side. I got -x squared minus 4y squared greater than or equal to -36. I'm going to divide both sides of the inequality for -36. And I got negative 9 divided by negative 36 x squared plus negative 4 divided by negative 36 y squared less than or equal to 1. So the coefficient of x squared is 4, so x squared over 4 plus y squared over 9 less than or equal to 1. So the domain of the function is on the point x comma y in R2 such that x squared over 4 plus y squared over 9 less than or equal to 1. Again, visualize this domain. We're going to see an ellipse. This is x, this is y, this is the origin. So the ellipse is going to be where the smaller side is along the x-axis and the longer side is going to be in the y-axis. So you need 2 on the shorter side and 3 on the longer side. So technically this is an ellipse. And the domain of the function consists of all the points inside this ellipse, including the boundaries. Okay. Now, similar to the first example, we're going to start with this information from the domain. So that is x squared over 4 plus y squared over 9 less than or equal to 1. This sum has to be greater than or equal to 0. We're going to solve this inequality such that it can go back to the form of 9x squared and 4y squared. So to do so, I want to mimic the functions given to us here, that is square root of 36 minus 9x squared minus 4y squared. So to get the negative 9x squared, negative 4y squared, I'm going to multiply negative 36 on every term of the inequality. When you multiply a negative number, the inequality direction will switch. So I have negative 36 less than or equal to negative 9x squared minus 4y squared less than or equal to 0. And to get 36 minus 9y squared minus 4y squared, I'm going to add 36 for every term in the inequality. And I get 36 minus 36 less than or equal to 36 minus 9x squared minus 4y squared less than or equal to 36. Or I get 0 less than or equal to 36 minus 9x squared minus 4y squared less than or equal to 36. Now I'm going to take the square root of this middle term, and I get 0 less than or equal to square root of 36 minus 9x squared minus 4y squared less than or equal to 6. And that is z greater than or equal to 0 less than or equal to 6. So that is the range of the functions. Is the set consists of all the points z on the real line such that z is between 0 and 6. Now we have one last example in this category where you want to find the domain and range of the functions. So for the domain of this rational functions, right, so this is a fraction, you don't want the denominator to be equal to 0. So the domain is that of x, y different from 0, implying that x has to be different from 0 and y is different from 0. So the domain of the function consists of all the points x, y in R2 such that x different from 0 and y is different from 0. This information tells you that you take all the points in R2 such that you just avoid the axis. Right? You don't want to collect any point on the x-axis or any point on the y-axis at all. So here, instead of a solid line, I have the dotted line. And I'm going to choose all the points in the quadrant. Alright, so I choose all the points in R2 except along the x-axis and along the y-axis. Now for the range of the functions, there's some restrictions here we must follow. So 1 over xy cannot be equal to 0 because x and y in a way is the vertical asymptote, and you cannot get to the vertical asymptote or cross the vertical asymptote at all. Then range of the function consists of all the point on the real line such that z is different from 0. You don't want 0. Or in the interval notation, you can write this as the interval from negative infinity to 0 union with 0 to positive infinity. So that's it for us when finding the domain and range of the function. We